The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is the first of a couple of lectures on group theory. Now, most of you have seen group theory and know group theory, and so I'm going to go very fast. And I'm also probably not going to go very deep because it's really hard to lecture on group theory unless you're going to do it right. Let me just start out with a story. When I was a freshman at Amherst College, I ended up doing research for an inorganic chemist by the name of Cooper Langford. And in one of my first conversations with him, I don't know quite why it happened this way, but I asked him a question about what transition is allowed, or somehow we got to that, and he took out a little scrap of paper and he did a little group theory on this scrap of paper and said, this is allowed and this is forbidden. And I'm sure there's more to the story, but I just remember that scrap of paper and being incredibly impressed. And that's really when I decided that I wanted to be a spectroscopist, because the idea of being able to make a decision based on something you can scribble on a piece of paper, which was not obvious, really appealed to me. So this is how you do that. And so let's talk about why we want group theory. We'd like to be able to know about selection rules. Because everything we do in quantum mechanics involves setting up some kind of a matrix to represent the structure of a system, or to calculate transitions, which transitions are allowed. And so we need to have something that's a generalization on even versus odd integrands. And so group theory is that generalization. We'd also like to be able to construct functions which have well-defined symmetry classifications. And so projection operators are a convenient way of doing that. One of the main things we're going to do in today's lecture is set up the structure that enables us to say what is the nature of molecular vibrations. So starting out with a picture of the molecule, you know what the geometric structure is or might be. And sometimes the issue is, well, how do we decide among possible geometric structures, qualitatively different ones? Is there something about the different qualitative structures that provides an unambiguous experimental observable that says this is D3H, and is D3H a possibility? Is that a legal? C3H is a possibility. D3, I don't know. But you decide between various qualitative geometries. And so this lecture is about how do we use group theory to construct and reduce reducible representations which contain information about what a molecule can do to irreducible representations that are the fundamental symmetry species of the various vibrations. And there's all sorts of wonderful tricks involved. Okay, so we're off to the races. And so we know that if we have some operator that commutes with the Hamiltonian, then we can simplify the Hamiltonian by constructing eigenfunctions of this simpler operator, because that will enable us to block diagonalize the Hamiltonian. Now there's three different levels. One is the full Hamiltonian commuting with some operator. And these are rigorous symmetries. And there are not that many of them. And usually they're pretty obvious. And that's nice, but we'd like to do more. Often we have some sort of zero-order Hamiltonian, some approximation. And those things generally have more symmetry, and it's easier to find operators that commute with the zero-order Hamiltonian. And so this provides a path towards constructing complete basis sets. Then there's a third thing, and in particular, C2 A, B, C. It's always true that the rotational Hamiltonian commutes with C2 rotations about the A, B, or C axes. Doesn't matter what the molecular symmetry is. The rotational Hamiltonian, which is expressed in terms of angular momenta components multiplying reciprocal inertial tensor elements in the principal axis system. In the principal axis system, the rotational Hamiltonian looks like a football or a frisbee. Doesn't matter whether it's a symmetric or asymmetric top. And you know that you take either one of those things and it's going to be, it's going to have C2 symmetry about any axis. And so the rotational Hamiltonian is going to commute with all these things. So there is going to be group theoretical features of rotational levels which are universal. And in addition to the group theoretical characteristics of the vibrations and translations. Okay. Yes?
Is that true even if you have axis switching with like large amplitude vibrations and things like that?
To the best of my knowledge, that, well, there's a problem. Okay, no, let me just, if we use symmetric tops, symmetric top basis set, then this is true. If we have asymmetric tops, we express the asymmetric top functions in terms of linear combinations of symmetric top basis functions. And so if we can classify the symmetric top functions, we can classify the asymmetric top. Now, when you talked about large amplitude motion, where you're blurring the distinction between rotation and vibration, I'm still talking about basis functions and the ability to classify basis functions. And I think that I'd better stop talking about this because I'm going to end up muddying the water. Okay, so we have this. Now, there's a whole bunch. We start out and we talk about point groups. Everybody learns group theory from the point of view of point groups. And point groups are a useful way of dealing with rigid objects. And they're not useful for describing large amplitude motions or transitions between electronic states where molecules have different shapes, qualitative shapes. A point group is called a point group because it consists of a bunch of symmetry operations, rotations, reflection planes, centers of inversion, where all of these symmetry operations intersect with or contain one point. The real symmetries in molecules are the complete nuclear permutation inversion group. Nuclear permutations, you have identical nuclei, you can permute them. Those have to correspond to rigorous symmetries. And there's a center, there is an inversion symmetry, not in the body, but with respect to the laboratory. And so these are the rigorous symmetry elements. Now, a subset of the permutations that are possible in a molecule are not feasible, because in order to permute those two things, you have to break bonds. And so it requires going over a very high barrier. They're not feasible, so we forget about them. But that corresponds to a degeneracy, or you have to somehow build a picture which incorporates those non-feasible permutations. So if we exclude those, we get what's called the molecular symmetry group. And the molecular symmetry group is isomorphic with the point group. And so you can usually use point group operations, point group ideas, even though they are an approximation. However, when you have really high excitation, really large amplitude motions, there become more and more of the elements of the CNPI group that become feasible, become relevant. And levels which when you say I've neglected a symmetry operation because it's non-feasible, that really means that the levels have a built-in, the energy states have a built-in degeneracy. And when what had been non-feasible becomes feasible, some of that degeneracy gets lifted. And that's really what we're interested in when we're looking at bond-breaking isomerization, because nothing could be more not feasible than breaking bonds. And so you have to get used to the idea that if you neglected a rigorous symmetry, you have said, I'm going to treat a state as if it were non-degenerate. And you can get away with that until that non-feasible operation becomes relevant. So we have the molecular symmetry group, and that takes us back to the point group. And usually there are no surprises. If you started out with ordinary point group theory, you can classify your states quite well. But you still have problems when you're facing transitions between electronic states where the equilibrium geometry is associated with different point groups. And there are a lot of ad hoc ways of trying to find your way around, when you're going from a higher symmetry to a lower symmetry, it's usually possible to sort of bullshit your way through this. But when you're going, say, between a C2H and a C2V, two groups that have the same dimensionality, when you're doing that, you really have to be careful. And it's there that keeping track of the permutations and inversions provide you with guidance. And often you have to go to a higher dimensional group in order to see the connection between two different point groups. So this is a beautiful and subtle thing, but you want to still see the beauty and power of just simple point group theory. And that's what I'll be talking about. Okay, so I assume that everybody has seen plenty of group theory. Yes, no? Everybody in the room. If anybody says no, I will say more. So you've seen some group theory. Okay, well, let's just touch on some high points. So we have symmetry operations. Rotations are denoted with capital C and an N. N is the order of the rotation. And so if you rotate by pi to, if that's a symmetry operation, that's C2. If you rotate by 2 pi over 3, that's C3, the number of clicks along a complete rotation. So there are various CNs. There are planes of symmetry, all of which are called sigma. And there are two kinds, well, there are three kinds of sigmas: sigma V, sigma H, and sigma D. Most of the symmetry planes that we see are sigma V. This is a plane that contains the highest order rotation. So high order rotation, benzene is C6, has a C6 rotation. And so sigma V, we always draw the rotation axis like this, and sigma V is a vertical plane. Sigma H is a horizontal plane. And sigma D is a vertical plane which bisects perpendicular C2 axes. So we have those things. Then we have I. I is inversion in the body frame. And that's different from big I, which is inversion in the laboratory. And people do confuse those. And this has to do with parity, and this has to do with GU symmetry. And it's it's almost as bad as saying nuclear to call the symmetry species associated with little I as parity. And it's very common. Okay, stop me. I mean, this is really, you're sitting here. I want you to know all of the actors. There's also improper rotations. Well, I should also say I is the same thing as, I have to look at that, C2 times sigma H. And but Sn is Cn sigma H. Now, often you have this is called an improper rotation. Often you have a higher order improper rotation than proper rotation. So Cn doesn't have to be a symmetry, but the product of two would be that. And so the inversion is S2. But we always give it a special name. And certain symmetry operations can commute with each other, and others don't. And you have to be careful about that. Reflections and rotations generally commute, but at least these two commute. Okay, so we have a group, and some of the properties of a group are closure. So we have a bunch of symmetry operations, R, and we can multiply R1 times R2. And when you do that, you get always another symmetry operation in the group. So there is a multiplication table among all the symmetries, which is complete. You can never get something outside the group. And if you have R1, R2, R3, you can put parentheses around any two. There's also an inverse. So every operation in a group, in a symmetry group, has to have an inverse. And so we have and there is also an identity operation, which is usually denoted E, but sometimes I. I is dangerous because I means something else, but not in point group land.
But E also means other things.
Yeah. So, okay, so there's a little bit of heterogeneity about notation, but there's an awful lot of universality. Okay, so now, you look at a molecule and you classify it according to symmetry operations present. Now, a symmetry operation is one where if you apply it to the molecule, well, let me say it again. You look at the molecule, you leave the room, somebody, your friend, applies a symmetry operation to the molecule. You come back, you can't tell that anything happened. So you classify the molecule according to which symmetry operations exist, and that enables you to identify the point group. And there is a logical procedure for doing that, and that logical procedure is a table in Bernath's book, and you can do it. Usually we deal with such low order groups that it's not a very complicated matter. They're always C2H or C2V or C2. So, okay, so you classify the group. So the next thing is matrix representations. So we have objects that have a multiplication table. And so we'd like to represent these objects by matrices which have the same multiplication table. Now, same is a complicated word because it means that there is nothing in the multiplication table of these matrices which would be untrue with respect to the multiplication table of the operators. Sometimes the multiplication table has lost a lot of information. So 1 times 1 is always 1, and you can represent a lot. Yes. So there will be matrix representations. Now, we're particularly interested in geometric transformations. So what we want to do is to find a set of matrices which are equivalent to each of the symmetry operations. Equivalent is a complicated thing. So one way of doing that is to label each of the atoms in a molecule by 3 Cartesian coordinates. And then we build matrices that transform the coordinates of the atoms according to how the symmetry operation would move things. And that's the first thing we're going to do. But the nice thing about this is that when we create this 3n dimensional representation of the group by building geometric transformations of the 3n Cartesian coordinates that correspond to the n atoms, we're going to want to throw away a lot of information. And this is the beauty of it. And this is why my friend, Mr. Langford, was able to do this incredible calculation on a little tiny scrap of paper, because we don't care about the matrices, we care about their traces, their characters. And there's powerful things. So what we're going to do instead of, well, first we're going to actually solve for some of the matrices. But then we're going to learn some tricks for what do we really need to know to determine the thing we really need to know, the characters. And that's much, much less. And one can, without being good at geometry, one can very quickly work out how to calculate the characters, the traces of the matrices that we need. Okay, so now I have to do some formal stuff, which I don't like very much because I often get confused. Let's do this. So here is a vector. We represent it by x, y, z. And, but we can choose a better representation. We can say this is x1, e1 unit vector, x2, e2, x3, e3. So e1, e2, and e3 define an axis system. And x1, x2, and x3 are the coordinates in that axis system. And so we could write this as sum of I, xi, ei, hat. Now, suppose we have some symmetry operation operating on x1, x2, x3. Well, that will give us x1 prime, x2 prime, x3 prime. And so we want to find the matrix that represents this symmetry operation that, when applied to x1, x2, x3, gives us x1 prime, x2 prime, x3 prime. So we want to find this matrix that does that. So I guess I don't need to. So suppose we're interested in the plane that contains x1 and x2. Well, what does that do? Well, the plane that contains x1 and x2 takes x1 into x1, x2 into x2, and x3 into minus x3. So D sigma 1, 2 is equal to 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So simply by knowing what each of the symmetry operation does to coordinates, you can work out the matrices. And so this is, and we could also work out, suppose we have a rotation by theta about the x3 axis. So what would that do? Well, if we rotate about the x3 axis, x3 goes into x3, but x1 and x2 get mixed up. And so we can write this as cosine, and we don't need to write all three letters, cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. So you can work out what various operations do. Well, I said that you have to have an inverse of every operation. So what does the inverse of this look like? So what transformation would do that? So we have c theta 3 minus 1. What would that do? What would that? So instead of rotating by theta, we rotate by minus theta. Cosines don't change. They don't care about plus theta and minus theta, but sines do. And so we get c theta minus s theta, c theta, 1. Notice that this is the transpose of that. Notice also that the rows and columns are normalized to 1, and the rows and columns are mutually orthogonal. Those are the properties of a unitary matrix. We know if we have a unitary matrix, if we want to perform a similarity transformation, we know that's a similarity transformation on some that it's easy to perform a similarity transformation which involves sandwiching an operator between u and u minus 1 and u. If the transformation operator is unitary, then you can get the inverse simply by taking the conjugate transpose. If the operator is, if the matrix is real, then you don't need the conjugate transpose, you just need the transpose. And so u minus 1 is equal to u dagger, ut, sorry. Okay, so we know an awful lot. We have transformations among on operators. We have multiplication of operators. We know that the matrix representations have to be unitary. And we know about what unitary is, normalization, and orthogonal. Okay. Okay, so now we're ready to be able to set up matrix representations of symmetry operations on a molecule using anything about the molecule that we want to use to generate a representation. So we attach to the molecule a bunch of basis vectors. So at each atom or each bond, anything we want to do. I mean, for example, for benzene, we can be really masochistic and have three Cartesian coordinates for each hydrogen and for each carbon. Or we can say, I'm only going to be interested in these 6 bonds, or in these 6 bonds. Or I'm going to look at perpendicular, I'm going to look at motions of the carbon atom perpendicular to the plane, and there's 6 of them. Or I can look at the motions of the hydrogen atom perpendicular to the plane. Or bending. Anything you want, and it doesn't have to be linearly independent. You can just dress up the molecule with a bunch of things that you're going to transform using the symmetry operations. And then using the simplification of not writing the D matrices that affect this transformation, but the traces of these D matrices, one can do this amazingly fast. And I mean, if you have 6 carbon-carbon bonds, you can't have 6 linearly independent bond lengths because 5 of them will determine the 6th. So there's going to be some over-completeness about some of these cartoons. But often you want to ask questions. For example, you want to ask questions of how many modes are confined to a plane? Of the 3n minus 6 normal modes, which ones conserve planar symmetry? Which modes are uniquely bending modes? Which modes don't involve hydrogens and not carbons or something like that? If there's any, well, this would be hard, but any question you want to ask that involves classifying the normal modes according to what is their content, you will find amazingly powerful results that come from practically nothing. Okay. So I'm just going to skip over this active versus passive because it's been scaring me, and you're going to have to sort this out for yourself. And I'll start. So we have matrices, and we're going to simplify matrices to characters. And so suppose we have a 3n by 3n dimensional matrix. That would be the complete thing that you would use. And so we have a matrix which will describe what any symmetry operation does to, say, the 3n Cartesian coordinates attached to the atoms. And we can just take the sum of the diagonal elements of these matrices, and that's called the character. It turns out that I'm getting ahead of myself, but I just have to say it. What's unique about a matrix? Suppose you have a 3n by 3n dimensional matrix. Well, it will have 3n eigenvalues. You perform a similarity transformation on that matrix, it'll have the same 3n eigenvalues. The trace of a matrix is invariant under similarity transformations. It's just the sum of the eigenvalues. The determinant of a matrix is invariant because it's the product of the eigenvalues. And so the information that is contained in a matrix, it may be sufficient to reduce our concerns to just the sum of the diagonal elements of each matrix. And so with that statement, I'm going to make the bold and useful comment that, okay, how do we construct a 3n dimensional representation of a molecule where the atoms are not all located at the center? So the first thing that you do is you say, okay, suppose atom alpha and atom beta are exchanged by the symmetry operation. Well, the matrix that does that is going to have an alpha block and a beta block, and in between there's an alpha beta block. And so all the information about the exchange of alpha and beta are out here. So if alpha and beta are exchanged, the coordinates of alpha and the coordinates of beta do not contribute to the trace. This is the most wonderful thing because it enables you to look at a molecule, and almost all the symmetry operations involve exchanges of atoms. In fact, only the atoms that lie on a symmetry element, like in a plane or along a rotation axis or at the center of inversion, only those atoms you have to worry about. All the atoms that are permuted, they don't contribute to the trace of this D matrix for that symmetry operation, and so you can forget about them. And that's fantastic. So so all you need is a small number of 3 by 3 matrices that describe what each of the symmetry operations will do to atoms that are located in a plane or on the rotation axis. And You already know that. You could work that out yourself. So you don't have to be good at geometry to figure out how to write this block in this matrix, because it's irrelevant. So we're going to use a picture of the molecule to generate what we call a reducible representation. And this reducible representation will be a collection of D matrices corresponding to the different symmetry operations. Okay, so we have all of the symmetry operations, and each one is represented by a matrix which has the same dimension. Different matrices. Now, we can write this reducible matrix as a sum of what we call irreducible representations, which just corresponds to basically block diagonalizing all of the transformations. So each one of these matrices gets block diagonalized in exactly the same way. Now, you don't know that that's guaranteed. And the only way you can prove that it's guaranteed to be possible to do this is from what's called the great orthogonality theorem. But it is possible to find a transformation that block diagonalizes all of these matrices into submatrices of the same dimension. And then we can write the reducible representation that we can generate very easily by simple, it's hardly even, it's magic. You generate this thing, and then you can say that the matrix is the sum of these individual matrices arranged along the diagonal. So we should be able to write this reducible representation as a number, how many times the new irreducible representation appears in it. So we should be able to decompose every reducible representation into the irreducible representations that it's made up out of. Okay. Now, the great orthogonality theorem tells us how to do this and why we can do this and all that wonderful stuff. And I'll write it down, but we don't use it. We use the reduced form of it, which is much simpler and easier to remember. So the great orthogonality theorem, from which all of these group theoretical results can be derived, and which can be proven, but in a fairly tedious way. So this is the sum over symmetry operations. And so we have now the so this is a particular irreducible representation. These are the I and K row and column of that matrix. And then we have another irreducible representation. And we have J and M and R, same R, complex conjugate. So here are two sets of matrix elements. The great orthogonality theorem tells you that this product is G, the order of the group, which is the number of symmetry elements. And divided by n mu, the dimension of the muth irreducible representation, and then delta mu nu delta I j delta k m. So it says if you have two different irreducible representations, they're orthogonal in the sense of all the rows and all the columns. And so we have all of this, all of these orthogonalities in this little thing here. Okay. It's possible to prove that n nu squared is equal to g, where this is the dimension of this is the dimension of the nth irreducible representation. There's a certain number of irreducible representations. You sum over all of the orders of all of them, and you get g. This great orthogonality theorem can be simplified by simply taking the sum over the diagonal elements. And so we can write this reduced form of, well, let's just, so the character of the muth representation is just given by the sum over I d mu I of R. So that's just the sum of the diagonal elements. And the reduced form of the great orthogonality theorem is sum over symmetry elements chi mu R chi nu R star is equal to g times delta mu nu. So these characters are sort of a generalization of vectors. These characters are orthogonal because of that. And when you sum over the symmetry elements, you get g. And so this is the thing one uses, and it provides a basis for calculating the decomposition of a reducible representation into its irreducible representations. So I'm just stating these results because you could spend weeks deriving them, but the neat thing is applying them. What time is it? Okay. And so the way you apply them is we would like to know how many times each irreducible representation appears in a reducible representation. And so we have A nu, sum over nu, chi nu R. So we want to know what the number of times each irreducible representation appears in a reducible representation. And that's given through the great orthogonality theorem for characters as 1 over g. And this is the equation you'll always be using. R chi reducible chi nu star. So you have an element, you have, for a reducible representation, it's going to be a set of numbers. What am I going to, how am I going to call them? Number. Corresponding to R1, R2, etc. And so both the reducible representation and the irreducible representation is the same number of numbers. So you just take these vectors and multiply them and divide by the order of the group, and you get the number of times a particular irreducible representation appears in a reducible representation. There's extra simplification, and we have, you don't need this, but since the character tables are always arranged in this way, we have the operations, the symmetry operations can be divided into classes. How do we know a class? Well, what we do is we say, okay, here is a symmetry operation. Let's calculate for all possible symmetry elements in the group this transformation. And what this will yield will be all of the members of the class that contains this guy. And so when you see, for example, the point group for C3V, the group that is ammonia, you see E2C3 3 sigma V. And then you see A1, A2, and E. And so there's the identity operation. It's in a class by itself. There are two C3s, C3 and C3 squared, or C3 and C3 inverse. There are 3 sigma V's. And so there's a class of dimension 1, class of dimension 2, class of dimension 3. And when you do that, you discover that the character table is square because the same number of classes, there are the same number of irreducible representation as there are number of classes. And that's wonderful. And so then in this character table, you have the characters for each of these. And so this is the totally symmetric representation. Nothing happens, and so you just get ones. And for A2, A2 is odd with respect to reflection planes, and even with respect to rotation. And E has this form. And there's some rules about this, but okay, so this is the character table. You have a set of numbers that you generate by, say, having a 3n dimensional representation, and so we get a reducible representation. And then we ask, how many times does A1 appear in it? How many times does A2? How many times does E appear in it? And it's really mechanical and simple, and the key is not screwing up, because this looks like a product of an element and the character of the reducible representation. And one goes by classes, so you have to multiply. If you're going to sum over classes rather than over the symmetry operations, you have to remember to multiply by these things. 90% of the errors that I've made in applying group theory has been forgetting to multiply by the order of the class, the number, yes, the order of the classes. And so you get, it works out sort of pretty well, and all of a sudden you get some representation appearing 3.5 times, or you come up short, and that is the error you're going to make. Okay, so I've more or less touched on the high points of what I've included in these notes. I do think that it would be useful to play around. I'm not going to make an assignment, but I recommend picking a molecule that has, well, benzene is too simple because the carbons and the hydrogens more or less do the same thing. There are certainly interesting things, but you ought to pick a molecule that has a relatively high symmetry, but where there's there's some interesting differences. I can't think of something offhand, but I suspect that the cyclohexane, where you have boat and chair forms, and so let's say take the chair form of cyclohexane and classify it, that's a relatively low order group. But whatever you do, I would recommend using various cartoons to describe, to pick out the kinds of motions that a molecule can have, and you'll be able to classify all of the vibrations, and there'll be certain irreducible representations that are pure bending and others that are pure planar stretching, or there'll be certain motions that you can name simply by doing group theory. And I don't know if cyclohexane is a good choice, but I cannot think off the top of my head of a good molecule that's not trivial but laborious like benzene, or trivial and not laborious like formaldehyde. Somewhere in between there's something really useful. And so anyway, I will continue with this on Wednesday.